Section 10.3 Regression. Now previously, the scatter plot helped us to see if there was a relationship between two variables. Then the correlation coefficient told us the strength of the linear relationship. The next step is to determine the equation of the regression line or line of best fit. And the reason we want to find the regression line is to see the specific trend in the data. We can say positive or negative, strong, moderate, or weak, but we want to have some numerical values there. We also want to be able to use the regression equation to make predictions about unknown values or future values. The line of best fit minimizes the vertical distance of each point to the line. So let me give you a quick visual of that. So let's say I have some data on my scatter plot and it follows this overall trend. And my line of best fit maybe goes through here. So these values here are pretty close, and this one's pretty close. So what we're trying to do is for each line, minimize that vertical distance. That one would go up there somewhere. Some are going to get very close, some are not going to get so close, but our objective is to minimize everybody's total distance. More specifically, when it comes down to the equation, we're minimizing the sums of squares of all the vertical distances. So because we use the line to predict values of y from values of x, we want it to be as close as possible to minimize error. Depending on the relationship, we might not get close at all. But the point and the way the equation works is to all those little distances, we want them to be as small as possible. Okay, now in example 1, before we get to anything very technical as far as a formula, we just want to practice recognizing where the line of best fit falls. So here we're being asked to draw a line of best fit for the scatter plot given below. This won't be an exact science, but basically that you're getting the trend that this data falls. So this one's positive, maybe moderate to weak, and a line of best fit will probably fall about there. It could be a little bit higher or lower. It might be tilted a little bit differently, but basically we can tell that the trend is increasing. Well, of course, we want something a little more accurate than just kind of guessing at the regression line. So we have this formula, and it should look pretty familiar to you compared to some other techniques you've learned in algebra. For the regression line, we have y hat equal to b sub 0 plus b1 times x. Does that look familiar at all? Hopefully it should. It should remind you of yx equals, or y rather, equals mx plus b. We're pretty familiar with that. We know that m is the slope, and b is the y-intercept. For some reason in statistics, it's written in a different order, and they chose b0 and b sub 1 rather than m and b. Don't ask me why, but this is the regression line, but otherwise it behaves the same way, slope and y-intercept. So b naught, or b sub 0, is the y-intercept, b sub 1 is the slope, x is the independent variable. You'll also hear the word predictor variable for x values, and y is the dependent or response variable. Now before we can use the regression equation, we have to calculate b naught and b sub 1. And probably those look just as intimidating as that R formula, but remember all the information is right there in the same place. So again, we'll need those sum of y, sum of x's, sum of x squared, all that stuff. And to minimize all the keying in we have to do, I figure we just work from the example we did previously with the women and the bone density. So we need to find, in order to find the regression equation, we have to find b naught and b sub 1. And I believe I got these mixed up. This actually should be b sub 1 here, and this one is b sub 0. So make sure you make that change. Okay. So if you have your calculator, you probably already have the statistics in there from those two lists, or you could just run them again. And we'll just start plugging in. So for b sub 1, n is 5. We had 5 observations. Sum of x, y was that big one. 190,973 minus sum of x, 242 times the sum of y, 4,039. All of that over 5 times sum of x squared, that's 12,232, minus sum of x, 242 quantity squared. When you're entering this in your calculator, I would encourage you to put parentheses here to isolate the numerator, then divide it by, and then do parentheses down here. Now, the way I wrote this, I know I used a lot of parentheses. You don't necessarily need those, but to distinguish the numerator from the denominator, that should make it come out correctly. So let's see what we get here. And I get 1,228.65. So to write my regression equation, y hat equal to b naught plus b sub 1x would be y hat equal to 1,228.65 minus 8.695x. So that's your regression equation. Okay. One other thing I wanted to make you aware of are some alternate formulas you can use if you have already calculated R or if it's given to you. So this just cuts down on all the summations and things you have to plug in. So we're going to recalculate the regression equation we just found with a given R, knowing that we already have it. So for the slope, and I have to start with the slope first because I need the slope to be able to do the y-intercept. So B1 equals R. Well, we found that before. Negative 0.94. This S sub y and S sub x, this represents the standard deviation of the y values, whereas of course this one represents the standard deviation of the x values. And those numbers are given right along with all the summation information that you had before. So if you go back to that screen or if you rerun your two-var you have the sum of x there. So I get, sum of y actually is on top. Or not sum of y, excuse me, standard deviation of y. So 105.43 over standard deviation of x, 11.39. Notice also in your calculator, I just want to point this out, you have a sigma x and a sigma y. The difference between those two, they're both standard deviation, but sigma is used if you're working with a population, whereas S is used if you're working with the sample. And most often for regression, we will be working with the sample, but just know the distinction between those two. Okay, so I think I have this set up right. R, our correlation coefficient, was given to us, or we found it earlier, negative 0.94. Standard deviation of the y is 105.43. Standard deviation of the x is 11.9. And if we divide all of that out, or multiply, we get negative 8.7. I have 0098, so I'll just leave it at negative 8.7. Which is pretty close to what we got before, 8.695. So that's pretty close. And I'm thinking if we had more decimal places in our standard deviations, that possibly we would have gotten even closer. Okay, now that takes care of B1, or B sub 1. Now to find the y-intercept, I'm going to use y bar and x bar, and these are the means, just like before. And again, those values can be found where you did all of your statistics. So, let's see, B sub 0, y bar is given as the average of the y's, 807.8, minus B1, which we found, times x bar, just 48.4. And I get 1,228.88, and that's quite close to what we got before. We got 1,228.65, so very, very close here. So the regression line would be minus 8.7x. So almost identical to what we had before. Okay, well now we can find the regression line. We know how to find b sub 0, we know how to find b sub 1, put those into y hat. Once we have the regression line, we want to use it to predict unknown values. So take a look at example 5. The following table gives the weeks of gestation and corresponding birth weights for a sample of 14 babies. The regression line is given by y hat equal to negative 17.89 plus 0.66x. So all that data there, somebody else did the work and they found b naught and b sub 1 and they put it all together, and that's the regression equation that they got. We even have a scatter plot and the regression line is already drawn. So with that information, we're going to take a look at the questions down here. A, according to the regression equation, for an increase of 1 week in gestation, the baby's weight increases by how many pounds? So this question, what it's saying is, for every week, so from 32 to 33, how many 1 week passes, how much weight is the baby expected to gain? Well, really, all that's asking is, what's the slope? And the slope is sitting right there for us next to x, so that is 0.66 pounds, or about 2/3 of a pound. So, of course, this doesn't happen with every baby or every pregnancy, but the general trend is for every week that the baby stays in its mother's womb, it's going to gain about 2/3 of a pound. All right, B. From the data, what is the observed weight of a baby born at 37 weeks gestation? So this question is asking me to look at the actual data that has already happened. And if I go back to my table, at 37 weeks, we had a baby that was born weighing 5.3 pounds. So that's all we need to do there. Okay, and C, from the regression equation, what is the predicted weight of a baby born at 37 weeks? So now they're asking me to use the equation to say what a baby might weigh given that it's born at 37 weeks. So again, this is not what it should weigh or what it has to weigh, but just overall trend-wise what it probably or what it might weigh. So here's my regression equation. Y hat equals negative 17.89 plus 0.66x. So what am I supposed to do with that 37? Well, since that's the number of weeks, and that corresponds to the independent variable x, we'll plug that in. So negative 17.86 plus 0.66 times 37. And I'm thinking we should get somewhere in the ballpark of what we saw in the observed value. The observed value had a baby born at 37 weeks, 5.3 pounds. Let's see what we get here. And I get 6.56, which is a little bit more than what I expected. It's still correct, but it's a little bit different. It's a little further away than I expected it to be. Well, here's the reason why. The data value of 37 weeks gestation and 5.3 pounds is right here. Notice how far away it is from the regression line. That's would explain why there's such a difference between the observed value and the predicted value that we got. Now, perhaps if we had more data, or more data would help to give us a better sense of what's going on. It could change our regression line a little bit, and maybe that observation wouldn't be so different, or maybe that baby was just a little underweight which there's nothing wrong with that, but just in the general trend of how it goes, that baby's just a little bit small. So the correct answer using the regression equation is 6.56, but that doesn't mean anything's necessarily wrong. It just is not as close to the observed value that we had previously.